high entropy alloys are promising the multi-component alloys with a unique combination of the novel microstructure and excellent properties. However, there are still certain limitations in the fabrication of the high entropy alloys by the conventional methods. Additive manufacturers high entropy alloys exhibit optimized microstructure and improved properties, and they are significantly increasing the trend on the application of additive manufacturing techniques for producing high entropy alloys in recent years. This review summarized the additive manufactured high entropy alloys in terms of the microstructure, characteristics, mechanical, and some functional property reported so far, and provides readers with a fundamental understanding of this research field. We first briefly review the application of the additive manufacturing methods and applied it to high entropy alloy system. Then the microstructure, including the relative density, residence stress, grain structure, texture, and dislocation network, element distribution, precipitations, and influence of the positron on the microstructural evolution. Next, the mechanical properties consisting of the hardness, tensile properties, compressive properties, cryogenic and high temperature properties, fatigue properties, grief behavior, post-treatment effects, and the strengthening mechanism analyzed. Thereafter, emerging functional properties of additive manufacturing high entropy alloys, namely the corrosion resistance, oxidation behavior, magnetic properties, as well as hydrogen storage properties, are discussed respectively. Finally, the current challenge and future work are proposed based on the current research status of this topic. High entropy alloys, also referred as the multiple principal element alloy or complex concentrated alloy, was firstly reported by Yet and Kato in 2004, which was defined originally as an alloy that contained more than 5 principal elements, with the concentration of H between 5 to 35%. Recently, the concept of high entropy alloy has been extended to an alloy with four principal elements as well. The underlying mechanism behind high entropy alloys is to minimize the leaf-free energy through the balance between enthalpy and entropy. To be specific, when a solid solution is formed from the multiple elements, the change of the configuration entropy is larger than that of most metallic materials, resulting in the formation of random solid solutions during the solidification process instead of the competing intermetallics of other complex phases. Generally, high entropy alloys exhibit a simple solid solution phase, such as the body-centered cubic, face-centered cubic, or hexagonal closed packing HCP structures. The combination of the high entropy servers, lattice distortions, split diffusions, short-range orderings, and cocktail effects contributes to the high phase stability and excellent performance of high entropy alloys, such as the combination of high yield strength and high ductility, excellent strength retention of cryogenic and elevated temperatures, excellent thermal stability, high resistance to corrosion, oxidation, wear, and fatigue. The multi-component high entropy alloys are typically produced by the conventional induction melting or vacuum arc melting for low risk with the casting, which require repeated remelting to achieve chemical homogeneity with a cooling rate 10 to 20 Kelvin per second. Conventional casting usually causes significant phase separation during the fabrication process of high entropy alloys, where the post-treatment process is usually required to further adjust the microstructure for precise properties. Besides, it is still difficult to overcome the inherent inherent complexity and high degree of control needed to produce homogeneous bulk alloys, and in the industry by traditional manufacturing routes. Therefore, there is an urgent need to develop effective and efficient techniques to fabricate the new class of alloys, among which the additive manufacturing methods can generate fast cooling and solidification rates and enable production of the complex geometries, as well as the design of high freedom have shown great potentials for producing high entropy alloys at high performance energy engineering materials. IMs now also known as the rapid prototyping or 3D printing has developed rapidly in the past few decades due to its ability to directly produce 3D parts layer by layer with unique shaping dimension based on the computerized design, case design model. AN is especially suitable for fabricating geometrically complex parts with less consumption time, with some advantage. AM has been applied with almost all fields, including automotive, aerospace, machinery, electronics, medical industries, and building construction. There are several AM techniques available for fabrication and production of the metallic materials, mainly including the selected laser melting depositions, selected electron beam melting, and wire additive manufacturing methods. Each of these methods has its own characteristics, which will be briefly summarized as follows. Selected laser melting, also known as laser beam melting or laser powder bed fusions, is the most widely used powder bed-based AM technique where during the selected laser melting process, a laser beam is used for melting and fusing the metal powders together. A thin layer of powder is spread evenly over the substrate or previously deposited layer, and subsequently the laser beam selectively melt and fuse the powder particles as dedicated by the AutoCAD models. For the selected laser melting technique require several process parameters, mainly the powder, mainly is the laser power, laser scanning speed, layer thickness, arching distance, scanning strategy have to be carefully adjusted to fabricate defect-free parts with optimized microstructure and properties. Depending on the reactivity of the used metallic powder, the selected laser melting process is usually performed in a closed chamber, filled with an inert atmosphere such as argon or nitrogen. Additionally, the beer chamber is also subject to an overpressure condition, which both help minimize oxygen contamination during the manufacturing process. A high cooling rate ranging from the 10.4 to 10.6 Kelvin per second could be achieved during the selected laser melting process. By ensuring the quality of the metallic powder, a precise dimensional control and with final homogeneity of the fabricated parts could be warranted with optimized processing parameters during this AM process. Laser melting directed is another laser-based AM method with a powder feed system instead, which allow higher flexibility of both port production via adjusting the raw material. Laser melting direction is also referred as laser engineering, shape, direct laser fabrication, direct metal deposition, and direct laser deposition, direct laser energy depositions, and laser directed energy depositions. In some literatures, using the laser melting direction process, metallic powders are dynamically fed into the laser beam spot and melted together with the previously deposited layer to build up the sustained structures. The layer melting process is usually protected from oxidation by applying protection gas such as the argon or nitrogen. This method can apply to or through hoppers with different feeders, which is particularly attractive for the fabrication of high entropy alloys at the requirement of the pre-alloyed powder can be avoided by using elemental powders at feedstocks. At the same time, it is possible to produce both chemically homogeneous and compositionally gradient materials by controlling the powder supply for different hopper and institute alloyings under optimizing the processing condition. Compares with the selected laser melting technology. Laser melting direction provides a higher deposition rate, allows building quick bulk samples of large dimensions. One problem is to be aware of this method is the generated chemical composition may be deviate from the starting powder composition because of the evaporation of some elements during the process. Electron beam melting is powder bed fusion technology with a higher power electron beam that function, at heating source to melt and fuse with the metallic powder under vacuum, also referred as selective electron beam melting. In some literatures, electron beam melting has a similar working principle with selective melting selected laser melting, both of which use the layer by layer method to melt and fuse metallic powders. The electron beam melting process is carried out in a high vacuum atmosphere where the oxidation of the fabricated parts is unusually averted. During the electron beam melting process, preheating the powder bed is needed in order to prevent the structural deformation of the build parts caused by the resident thermal threat, which will affect the cooling rate and final microstructure. In as manufacturers components, more processed parameters are involved in the electron beam melting process. One RIM technique, including the beam power, beam focus, beam diameter, beam line spacing, beam scanning speed, plate temperature, preheating temperature, control trajectory, and scanning trajectory. This electron beam melting process is fundamentally so slow and thus makes the fabricated parts is very expensive. In addition, there are restrictions in terms of the size of the build parts and minimum size of the cells in the lattice structures. Essentially, essentially different from the metal powder-based AM techniques mentioned above. One process employs an electric arc as the heat source and material filler-wise as the feedstock materials, which we consider is to be a cost-effective technology. Using one process of high entropy alloys, considering desorized compositions, a combined cathode of the commercially available metal wires is usually used as raw material, which can be fully melted to avoid metal loss due to the unfused powder. In the case of applying powder-based AM methods. Besides, RAM also has the advantage of high deposition rate, low equipment and material costs, enabling it suitable for the production of large-scale metal components. Therefore, RAM has emerged as a promising emitters for the high-entropy alloys since last year. However, the use of RAM to manufacture metal components also leads to drawbacks such as the poor sub-optical surface quality, insufficient dimension accuracy, and calculation low density due to the vigorous Nepro interaction. In addition, though, the relatively slow cooling rate and low heat short spot of the RAM may result in larger tensile resident threat and distortion for the fabricated parts. The rapid solidification during above mentioned while AM process can restrict the composition of segregations and the formation of the brittle intermetallic in the build parts, contributing to the strengthening effects through grain refinements, presenting great potential for fabricating high entropy alloys, which has gained increasing interest in the research community. It is worth noting that some of the previous AM research focused on high entropy alloys coatings. Here we highlight the microstructure and properties of bulk high entropy alloys fabricated by AM technique. The first research work of additive manufacturing high entropy alloys was conducted by Kunz in 2013. Subsequently, publication of this topic have shown a substantially increasing number over the last 10 years. See Figure 1, especially since 2019. It should be noticed that there are several review papers focusing on the high additive manufacturing for high entropy alloys, which have provided important information on the microstructure and properties of high entropy alloys. However, the systematic review article with regard to the detailed success on the microstructural characterization, mechanical and functional performance of IM for high entropy alloys is still lacking in current work. We reviewed application of the different IM technique in the different high entropy alloy system from the aspect of these detailed microstructure and the properties in the following sections, providing a timely and comprehensive summary of this promising research topic to guide further developments, especially specification, a general summary of the applied alloy element and details of high entropy alloy system in AM field will be introduced in section 2, and then section 3 reviews the microstructural crystallization of additive manufacturing high entropy alloys from the perspective of relative density, resident threats, crystal features, dislocation, network, element distribution, phase, and precipitations, as well as the effects of the post-treatment effects. After that, the thermal properties, the mechanical properties of printed high-entropy alloy parts will be revealed in terms of hardness, tensile, and compressive property, cryogenics and high-temperature properties, material and quick behavior, as well as the post-treatment effects in section 4. Moreover, Moreover, multiple strengthening mechanisms will also be discussed in section 4. The functional properties, including the corrosion resistance, oxidation behavior, magnetic and hydrogen storage properties of additive manufacturing high entropy alloys will be revealed in section 5. Finally, the current challenges and the future opportunities in this research field are proposed based on the current development trend.